Okay, thank you for the introduction. So yes, I will be talking about our work on this DPS protocol. This is work together with Marcus, Vilasini, and Ramona. And first, before I start, a little warning maybe. I will be sweeping some details under the rug here, just to make it more accessible. The full details can be found in our paper, however. So if something seems a little bit off, maybe that's because it is. So don't read maybe too carefully. But anyway, it should provide a decent overview of the proof technique and the features of our proof. Okay, so let's start with the setup of our problem. So we have the basic sketch here. So it's a QKD scheme, and as always, you have our two honest parties, Alice and Bob. And in the middle, we have Eve. And so then what happens is that in every round, Alice chooses a random bit U and encodes it in the face of a coherent state. So she produces either plus alpha or minus alpha, depending on her key bit U. Then she sends this state through Eve's attack channel. Eve does whatever she wants with it. And then at some point, it comes to Bob, who does a phase measurement on these states. And so to illustrate how this works, let's look at an example. So suppose now that U is equal to 1, then Bob will receive a state minus alpha. And if now from the previous round he got the state plus alpha, what will happen down here is that on one of the arms we will get constructive interference, and on the other arm we get destructive interference. So one detector will click and the other one will remain dark. And so in this way, Bob measures the relative phase between these two signals. And if they had the same phase, so both minus or both plus, then the other detector would have lit up. And then, as in any QKD protocol, if Alice and Bob see too many errors, they conclude that Eve was listening, and so they abort the protocol. And I would like to draw your attention to this kind of interesting structure on Bob's measurement, where in every round, some amount of light here is split off and then recombined in the next round to produce the key bit. And so it has a lot more complicated structure than, let's say, standard BB84, where Bob's measurement is the same in every round. And as a result, a lot of security techniques, such as the post-selection technique or Definetti arguments, don't work for this protocol because of this structure on Bob's measurements. And this is why, from a theory point of view, it's interesting. It's also interesting from a practical point of view because the components here are fairly readily available for implementation. Okay, so before we get into the meat of our work, let me give a little bit of background on what we actually try to do in a security proof. We have our state here, rho, which is a state at the end of the protocol. And we want that it is close to some product state that is maximally mixed on Alice's side. And there's a very nice theorem called the leftover hashing lemma that says this can be achieved as long as this smoothman entropy is sufficiently large. So if this quantity here is large, this exponential will be small, and so delta will also be small, and the two states are close to each other. And so all of this is to say we need a lower bound on this smoothman entropy. This is sort of the motivation for the people who have never seen a sort of finite size security proof, and this is why we care about this quantity. And so thankfully for evaluating these smoothman entropies, there are several tools, and the one we use is this entropy accumulation theorem, or the generalized version of it. And so here we have a sketch of this entropy accumulation theorem. We have some initial state that gets fed through channels M1 to Mn. We produce some classical outputs, X1 through Xn, and we also have some quantum side information here, E0 to En. And then the entropy accumulation theorem tells us that the smoothman entropy of these outputs, conditioned on the final side information, is lower bounded by n times the single round entropy up to some smaller order correction terms. And so here H is this single round von Neumann entropy. Now, if we want to apply this theorem, what we need is we need to answer two questions. The first one is, what are these channels? And the second one is, how do we compute this single round entropy? And of course, the answer to the second question will depend on the first, so we will tackle them in this order. This will be the remaining part of the proof. Okay, so let's start with the first question. What are the channels? So generically, ETH could apply one big CPTP map to all of the Alice's signals, here labeled S1 to Sn, produce some new signals, S1 through Sn for Bob, and also keep some side information for herself. And at this point, we don't have the necessary structure to apply the entropy accumulation theorem. So what we need is a condition that allows us to factorize this map. And so if we now add the condition that ETH cannot signal from future rounds to previous rounds, then it can be shown that this map can be decomposed in this fashion. So this is a theorem that we also show in, I guess, version 2 of our paper, which will be on arXiv soon. But anyway, so if we have this condition, then we can always find this sort of decomposition of channels. So it starts to look a lot more like what we need for the entropy accumulation theorem. Okay, so then if we continue, we not only have ETH, but we also have our two honest parties. So let's consider Alice first. So Alice has some source and a phase modulator. And so abstractly, you can think of this as a CPTP map that produces a classical register U, which is Alice's raw qubit, and some signal state S. And so if we have these ones, we can sort of play Lego and put them up there, and we get the following picture. Then Bob's setup is a little bit more complicated. He first has this beam splitter that produces some memory register R prime. And this is this first map here that produces R prime and some other signal state, which is the part down here. And then afterwards, he takes the memory register from the last round and performs a phase coherence measurement, which is this map B here. And so we can again play Lego and get this picture now. We see here also this sort of complicated structure that I mentioned before, where in every round some light is split off for the next round, and then some light is split off again, and so on. And throughout this thing, we always sort of keep the phase coherence. We never break it, which is an important difference to previous works, is that we can sort of deal with this kind of setup. And so now to answer the first question, we draw some boxes and call these channels here M1 through Mn. And we apply the entropy accumulation theorem with the following identification. So with this, we have the first question answered. And so we can now continue to the answering the second question, which is this single round von Neumann entropy. So let's again take one of our channels here. I have slightly abbreviated the names of the registers to make it fit here on the side. And we then switch to an entanglement-based picture, which is done oftentimes in QKD security proofs. That is, we say, instead of preparing the states plus alpha minus alpha with probability 50-50, what Alice could do is she could prepare this entangled state and then measure the register U in the computational basis to obtain her raw qubit. And the post-measurement state would be the same as if she had prepared the probabilistic mixture. And then after she has done this, Bob will receive some state rho SR. So S is this part down here that I haven't labeled. And R is the memory from the previous round. And he performs this phase coherence measurement here, which is this map B. So at this point, we still have one big problem for evaluating the entropy, which is that these memory system R and also the signal system S here, they are photonic systems, so they're infinite dimensional. And we cannot perform numerics on infinite dimensional systems. And so we use another well-known technique called squashing. And so the idea is that you take this map B here and you replace it with first some squashing operation lambda, and then some operation B tilde, which acts on these systems R tilde and S tilde, which are qubit systems. So this B tilde here is a finite dimensional operation. And the trick then is that we draw a box around this whole thing up here and call this some other map, E tilde. And so you see now that for every attack E that ETH could perform, there is an attack E tilde that is at least as strong on this now qubit-based protocol. And so if we want to evaluate the entropy, we can evaluate it on these finite dimensional systems down here. And so this makes the problem tractable numerically. And usually this would be enough for sort of security proofs. However, we have an additional sort of structure on this map E tilde here, or let's say on E, that it does not signal from up here, from S to this R down here. And we want this sort of property to be retained under this squashing operation. So what we want is this squashing operation should not introduce any signaling where there was none before. And so we require that the squashing operation does not signal from S to R tilde. And in our paper, we show that such a squashing operation indeed exists, and also this map B tilde exists. This is a non-trivial statement for most measurement operators. Squashing operations don't exist, and even if they exist, they don't necessarily need to have this non-signaling property. So this really is a theorem that you have to prove, but we give explicit construction of this squashing operation in our paper. And so we can make this substitution here. And so then if we have this property note, then this whole E tilde does not signal from S to R tilde. Okay, and so then finally to compute the entropy, we need to optimize overall attack channels. So we have the following optimization problem: minimize the entropy evaluated on the post channel state, and we minimize this overall possible such channels E tilde that do not signal from S to R tilde. And again, here nu is the state after Alice and Bob measured is the output of ETH's attack channel. And this kind of problems can be solved using well-known optimization techniques. There's SDP relaxations of this problem. There are ways to tackle it more directly. So this one is fairly cookie cutter at this point. Okay. So now let's continue to the results and discussion part of this talk. So the first one is we get key rates. So here in the dotted line, you see the asymptotic key rate. We observe that it scales linearly as a function of the transmittance. This is in agreement with known upper bounds on the scaling of these sorts of key rates for standard prepare measure protocols. And we of course also see that as the number of rounds increases, it approaches the asymptotic key rate as you would expect. Now, more interestingly, there has been prior work on this protocol regarding upper bounds as well. And so in particular, we have this series of works by Marcus Curti and collaborators where they devise attacks on this DPS protocol. And what they derive in this work is this red region here, where on the horizontal axis you have the transmittance, and on the vertical axis you have the quantum bit error rate, the QBER. And in this red region, they show that the differential phase shift protocol is insecure because there is an attack for these noise parameters that gives ETH all of the information. We can sort of do the same thing for our security proof, and we get this blue region where we claim the protocol is secure. And so you see here, there's this part where the two overlap. So this means they have an attack, and we claim it's secure. This might first seem like a contradiction, but it's not, because we have this additional condition on ETH's attack that she does not signal from future rounds to previous rounds. And this attack by Marcus Curti does not satisfy this condition, it violates it. And so we don't necessarily expect our security proof to apply. However, note that this condition that ETH does not signal from future to previous rounds is trivially satisfied for collective attacks because they don't signal in either direction. And so therefore we can conclude that for DPS, the coherent attacks are strictly stronger than the collective attacks, which to our knowledge is the first time this has been observed for a device-dependent QKD protocol, which is sort of a surprising feature because for most QKD protocols, let's say BB84 or B92 or whatever you want, this tends to be not true. The coherent attacks are not stronger in the asymptotic regime than the collective attacks. Okay, and so with this I can come to my conclusion. So the first point is, with this generalized entropy accumulation theorem, we are able to prove security of this protocol. Doing so required us to put a constraint on ETH's attack, mostly, namely that she does not signal from future to previous rounds. With this constraint, we can use tools from causality to both define the channels and then also to evaluate the signal round entropy there are some nice tools that sort of allow us to tackle this optimization problem. Then lastly, a constraint of this form is really necessary, this non-signaling constraint, if we want to reduce the analysis of this protocol to collective attacks, which the entropy accumulation theorem does. Pretty much all other techniques I know of more or less do as well. So in that sense, this constraint is not a sort of artifact of our proof technique, but it really is a feature that is inherent to the protocol. And with this, I'm at the end, and I think we have maybe some time for questions and answers. Thank you.
Yeah, thank you, Martin, for the great talk. Are there any questions?
Does this work? Oh, sorry. Just a clarifying question. So one of your slides said that you are assuming that Eve is generating a qubit and sending it along. What if Eve is actually extracting qubits out and not generating a signal? Is that also is that type of attack included in your analysis?
What do you mean with generate? Do you mean this sort of argument here?
Yes, the very last line. That we assume Eve's attack produces qubits, but what if Eve's attack actually reduces the qubits? Okay,
the statement here is that we can, without loss of generality, assume that Eve's attack does produce qubits by this squashing argument, where you can, basically the idea is that you have two protocols, the one you actually care about, and you have a qubit version of the protocol that you care about. And with this sort of argument, if you can find this squashing map, you can show that the qubit version, the simple version, is a lower bound on the actual original protocol. So in this case, you get lower bounds on the key rates. So we don't need to assume anything about sort of the dimension of the system of Eve's attack, but we have this sort of formal argument here which helps us then evaluate single round entropies. Does that help? You still look confused.
Yes, it does help. Sorry, I was still processing.
So I'll ask a question then while everyone else is thinking. Martin, can you say more about the construction of the squashing map?
Sure. I mean, one thing I can say is like, we're not the first people to do this sort of squashing arguments. And the squashing map that we find here is somewhat similar to known squashing maps for BV84, which at least for me was surprising. And for a long time, I didn't have hope that we could actually find this map. In the end, we managed. Yeah, I don't have like good ways of how you find this, apart from being lucky and doing some numerics. So if you can have the computer construct a squashing map for any finite number of sort of a finite photon number cutoff, and then try to guess some patterns, which surprisingly worked. And so if you want to see the squashing map, you can find it in the paper. We give explicit Krauss operators of this map. I didn't find any insight in staring at it. Maybe you do, but I don't have much more to say about this. I mean, for the argument, the structure of the map doesn't matter. All that matters is that it exists, that it has the properties that we want, namely this sort of non-signaling property here.